Right, okay, so in order to be able to follow the fetch execute cycle through, you actually need some specific instructions. Okay? Because when you get to, once you've decoded, there is then what you do next depends on what the instruction is and what format the instruction's got. Okay, so we're going to look at the fetch execute cycle with a simple instruction first, and I'm going to have to introduce addressing modes. So I'm going to have a mnemonic, an assembly language mnemonic. Remember, that's just a memory aid. So instead of using 01011, which might be LDA, so load a value to the accumulator, as a human, I can remember things like LDA better than 01011. Okay, so that would be the machine code opcode, and that's the assembly language equivalent. And that, remember, when we talk about low-level languages, there is, between assembly and machine code, there is that one-to-one mapping. So each instruction in assembly language is literally an instruction in machine code. Okay, so when people say they're machine code programming, what they mean is they're writing in assembly language, unless they're weird and they want to write it all in numbers, which you do sometimes want to write it in numbers. There you go. Right, so the other part we need to worry about is the operand. So then we've got, so I'm going to do this one first. Now, this is what we call immediate addressing. Now, the symbols that we use for this, they're different depending on what form of assembly language we use. And the exam board have not specified one because they decided to use Little Man Computer, which only has one addressing mode. So, in general, they'll explain to you, or they'll ask you about the addressing modes, the four that we've got to remember. There's loads more than that. The four standard ones, they'll ask you about them, or they'll ask you to identify which ones are being used. And there was a really tricksy Little Man Computer one that was like that, and we will look at that, because it was a stupid question, but it was a good question. It was a confusing question. So we're going to go through the fetch execute cycle, and we're going to see what happens after the decode stage. So we see what the control unit's got to carry out next, and we'll do that with the four different addressing modes. So we're covering addressing modes by doing the executing instructions. Okay, what was the first step in the fetch execute cycle? Where does everything start?
Wasn't it the value of the program counters copied to the MAR?
Right, okay, so step one, we do PC, we want to fetch something. So your brain should be saying to you, right, I want to fetch some data from memory, so I need to specify what location. As soon as you say that, you should be thinking, right, how do I specify location? Oh, it's something to do with the memory address register. Whatever's in there travels across the address bus and communicates with the memory controller, which we don't worry about how that works, but it does, okay, to say select that memory location. When we're starting a fetch execute cycle, we have a dedicated register that keeps track of where we're going to execute an instruction from next, and that is that program counter. Okay? When you first turn a computer on, the program counter will have 0 in it. So the memory address register will be loaded with 0, which will in general refer to a ROM location. Could refer to memory, RAM, but there'll be nothing in it. Okay, so you wouldn't get very far. Right, okay, so that's the first step. So we select a location. What's the next step?
Well, that would be the actually fetching the so going to the address.
Perform the first fetch.
Yeah.
We don't go to the address. Right, so the control unit issues a read. So it says to the data bus, read, and the data bus goes, okay, from whatever location I'm currently sat at. So we have MS to represent main store, because we're generalizing it. We're not saying it's cache or it's memory. We just talk to the memory controller and it goes, oh, that's in cache, you can have it from the cache. Or it goes, oh, bugger, that's in RAM, you'll have to get it from the RAM. Gets a bit more complicated if it's actually not in RAM at all and it's on virtual storage somewhere, and then the operating system has to do some work. Right, so we tend to sub-write it like that. So we say like the location given by the MAR in main store. So we treat it like a big array and we transfer it to the memory data register. Okay, so in order to make this a little bit more codey, let's say that this data is at memory location 150. So this is the memory address where that instruction is stored. Obviously it doesn't look like that, it does look like a number. Right, so that's the memory address of the instruction. So if we was to keep track, so I'm just going to do a little table here. So we got the program counter started off as 150, and I'm just going to do like a dry run thing. The memory address register, when we did step 1, I'm writing in there, okay, ended up with 150 in it. The memory data register is going to end up with something in it. What's the other registers? Current instruction register. 2 more. You need to be able to just ring these off. Accumulator. And then status register. The one that keeps track of what was the result of a calculation and where the interrupts come in as well. Among other things, but we don't go into the other things. Okay, so when we do the transfer, the MDR has whatever is at that memory location. So we're going to keep it in assembler mnemonics. So we're going to say LDA #7. Because this is the first part of the fetch, the control unit says, whatever's in there, I'm assuming it's an instruction. So it transfers it immediately. So we go MDR to current instruction register. So the current instruction register ends up with LDA 7. Right, so at this point, because of the current instruction register, it has this format. So this is the CIR. It has a format that allows it to hold an opcode and an operand, but the operand is actually 2 things, as we said last time. The operand is the address mode, so how to interpret the operand, and it's also the data that we're going to use for the addressing mode. Okay, so when we write this in assembler, the formatting of this bit gives us the addressing mode and the data. So the hash is just a substitute for saying immediate addressing in this assembly language format. The 7 is the data that we're using for the immediate addressing. Okay, right, so at this point we do a decode. So we've worked out it's a load to the accumulator. We've looked at the operand and we can see the addressing mode is immediate addressing. Now immediate addressing states that the data is the information you wanted. We don't have to do any more fetching from them. We don't have to go somewhere and pull a value. That's why it's called immediate. As soon as we've decoded, we know how long in bits or bytes the instruction is. So we know whether it takes 2 bytes, 1 byte, 3 bytes, 4 bytes, 10 bytes, which means we can increment the program counter. So it points to the next instruction in the sequence. We sort of abstract this quite a lot, and we might say the next instruction is at 151. But we're not saying how many bytes are used up to hold an instruction. All right, we're abstracting a little bit. We can look at it for real by looking at some proper assembly language, which we will do. So as soon as we've decoded, we know the size of the instruction, how many bytes it occupies, so we can increment the PC. So that can be a special addition unit that's dedicated to that, or it can be just kick the PC onto the data bus in the CPU, go to the ALU and add 1 and do it that way. Do an increment and then send it back. But we increment the PC. You mustn't increment the PC at the start because you don't know anything about the PC new value. Okay, so we do that, and then so we've done the fetch and the decode stage. Now we can do the execute. So in this instance, to do the execute, that's actually going to involve. So this is where. So we would just normally write stage 6 execute, and then we do stage 7 check for interrupt. But we can actually say what happens now. So for this particular instruction, and that's the logic that's built into the control unit, which is, I mean, I think I mentioned last time that it's the instruction set isn't hardwired. There's like a setup of logic circuits, but you write something called microcode, which is put on top. Okay, so there's like a programming language all to do with how the registers are manipulated and things. So in this example, to execute this, we've got to do a transfer. So the execute phase actually is transfer the operand data to the accumulator. So we take the 7 that was in our instruction and we say, oh yeah, go on then, put it in the accumulator. Then we can do the next step. So I'm not going to put a number against that because I'm trying to keep those numbers as the fetch execute cycle numbers. So once we've done that, we can then say, oh, let's just see if anybody needs our attention. Check for the interrupts. So in the exam, if they ask you for the general fetch execute, you're just doing steps 1 to 7. You say that's generally what happens. But actually the execute phase changes, obviously, depending on the instruction. Okay? Right, so that was immediate addressing. Any questions about that? That is, remember, if you want to tie that to high-level languages, immediate addressing is the same as a constant value. Why is it the same as a constant value? So in, let me just scroll across. We might, in a bit of code, we might say if A equals 1. Go on.
Is it because the immediate addressing, like the address, well, basically, the bit of code tells you exactly where the data is. It's not telling you to move anywhere else. It's like assigned to it.
No. Just looking at this if statement, I'm comparing with 1. I'm saying whatever's in A is a variable. I'm comparing it with 1. Every time I run that program, what value am I comparing A with?
1.
Why? Yeah, it's what we call a literal constant. I haven't defined a constant, but I'm saying that I've just typed that in the code. Now look at my assembly. I've put the instruction, I've put 7. Every time I assemble this code, that's always going to be a 7. So I've actually said 7. Literally 7. So it doesn't matter what I do, unless I do some weird self-modifying code, that value is always going to be 7. So immediate addressing is the same as providing a literal constant when we are doing high-level languages. Okay? It's funny, you look at your code for your projects and you'll have it littered with literal constants. Because that's how we do things. You know, if you're like saying, oh, I want to do something if the number's greater than 0, and you put that all the time. If we're talking about readable code and self-documenting code, you might replace that 0 with an actual defined constant with a name, just to make it more readable. But always think of immediate addressing as the same as providing a constant value. Okay, so I'm actually, with this one, a more appropriate pseudocode would have been to say, I had a variable called ACC, and I'm setting it to 7, which is effectively what I'm doing in assembly language. Okay, so that's immediate addressing. So let's have a look at the process again. So what I'll do is I'll rub all that out, because obviously I'm videoing this. I think I'm videoing it, yeah I am. Right, so if I rub this out and pick a different instruction, I'll do the same thing, load into the accumulator, but this time I'm going to use what we call immediate. Hang on, not immediate. Why's my brain just gone dead? Direct addressing. Ah dear. Direct addressing. My brain's gone dead because I'm tired. Right, so direct addressing. Now this is the one that Little Man Computer uses. It's the only one. Okay, so I'm going to write a couple of memory locations this time because I need this for this. Right, so I'll use 150 again. So I'm going to write this instruction at memory location 150. Change the number though. I'm going to put the number as 157. So I'm going to write it like that. So I'm going to hash in front of it this time. So this is direct addressing. So I'm going to put some dot dots, and then at memory location 157, I'm going to have the value 109. Okay, so these are just some instructions, but I don't care what they are. So I'm going to set my program counter to 150 again. Okay, and I'm just going to put a point and say that's where the PC is. So in this mode, this is where the operand data this time specifies an address. So this, talking again in high level language terms, this is like a variable. Okay, because remember, a variable is just a name given to a location in the computer's memory, which is exactly what this mode is. Okay, so let's have a look at the execution of this. So I'm not going to change any of these things, so it's the same thing. So program counter to the MAR, so 150 goes in the MAR, read the stuff in. So let's put the, I'll try and make this a bit wider this time because I was cramping it up. So PC, MAR, MDR, CIR, accumulate. I'm not worried about the status register. Right, so we start at 150, so that transfers across. We then do our read, so in the memory data register, what's the alternative name for that? Just one letter different. Buffer, memory buffer register, just in case they use it. Right, so we decode it, we increment the PC, so let's just abstract it and say, oh yeah, just move to the next memory location. So I'm just showing the overwrite there. We decode it and we say, oh right, okay, so with this time we've got to treat the data in the operand as an address. So when we get to this execute phase, we actually can't execute the instruction yet because we haven't got the data for the instruction. So how do we get the data? We know where it is, but how do we go and get that data? What steps are we going to carry out? So it wasn't, that's what we did last time when we had the immediate. Go for it.
So if you know the data is being held at 157, would that be copied to the MAR?
Yeah, exactly. If you've got an address where you know the data is, in order to access that, we need to select it. And the role, and this is why the roles of the registers is what you've got to learn. You think, right, okay, I want to select it. What register is responsible? Oh, the MAR. So I use the MAR to select a location. So I'm going to transfer the data to the MAR, which is why we have got a data bus inside the CPU to do inter-register transfers. Okay, so that would be the 157. So in the MAR, I will put 157. This is something that they may ask you to demonstrate. They may say, execute these 3 instructions in Little Man Computer or something, and they'll say, what's the status of the registers? So, particularly with an instruction like this, they would expect you to be able to show that actually the instruction was at 150 and we had to do another fetch. So there should be another address in the memory address register. So the next step, once we set that up, is to do the transfer again. So we do a fetch. So some instructions, the reason some instructions are quicker than others is because some instructions don't require multiple fetches. Okay? And that also comes into effect when you're dealing with bigger addresses and bigger data values. If you want to fetch a 64-bit data item when your data bus in your CPU has only got 32 bits, then you've got to do 2 fetches. So it's going to obviously take a longer amount of time, because even though the computer's running at like 2-3 gigahertz, there's still a time, you know, and it all adds up. So we just do a transfer. So I'll do it this time, instead of saying MAR, I'll do 157 just to show it, and that arrives at the memory data register. Oh look, what step did I miss out? Didn't copy to there, so I didn't copy the instruction. Right, and this also shows why we have a current instruction register. At GCSE we just ignored that. They weren't bothered. Although if you mentioned it, they were happy. But yeah, we just said, oh, the instruction you're executing is in the memory data register. Well, if it was this instruction, what's going to happen to the memory data register? It's going to get overwritten with 109, the thing we just fetched. That's why we have to have the current instruction register. That's why it's there. So that the control unit doesn't do a me and go, hang on, what was that instruction? It's gone. I didn't write it down. Yeah, it wouldn't be very quick if the computer had to write down instructions and things. Right, so we've got that there. So at this point, everything is loaded up. So to execute this instruction, now we've got the data, we can see the data is in place. We do a transfer. So this time it's a transfer from the memory data register to the accumulator. So we end up with 109. Then we can check for interrupts. Okay, so you can see, and straight away this should be saying to you, oh, immediate instructions, they're going to execute quicker. Because it was just one step, wasn't it? It was just transfer something that's already at the CPU to another register. So you can't do anything quicker than that. This one, right, so we've done a transfer, then we've had to read from the data bus, then we've done another transfer. So this bit, this is your bottleneck. Okay? Which is why we use cache. Because if we've written our program in a certain way that we're accessing recent memory locations, then we don't have to go all the way out to slow old RAM. We can go straight to the cache and pull it. But the CPU doesn't know about those things. It's a bit like when you're object-oriented programming, you do one job. The CPU isn't handling memory, there is a memory controller to handle that. So the CPU just says, oh, I don't care where it's coming from, it's just going to come along the data bus to me. I don't care whether it's come from 5 miles away or not. Just give me the data, and it's someone else's responsibility. So that's the one that Little Man Computer uses. And now what's quite weird when you're doing Little Man Computer problems, which we did a little bit of and we need to do a lot more of, is when you haven't got constants, it makes it really hard. You have to make up, remember we did variables just to represent the number 1 and 0, so you could do comparisons and things, and it's like, oh, really? So having variables sounds great, but if it's the only thing that you can do to store data, it's not mega. When you're programming, you can get around it, but it's just like, oh, it's a pain. But it does highlight that constants take storage and things like that. Right, okay, so that's the direct addressing. So there's 2 more. What's one of the other addressing modes? Indirect. So let's have a look at indirect. So let's rub all this out again. I'll try not to rub my table out this time, and I won't have to run it out again. Right, indirect. It's also got another name. Anyone remember it? No, we can't. We can't remember the name. It's vectored. comes from interrupt vectors. Okay, so put it back in pen mode, that'll help. Indirect addressing. So as its name, and there isn't an indirect or an indirect. There is just indirect addressing. So indirect addressing, also known as, oh dear, my writing's getting bad, even with this. So that's also got the alternative name of vector address. Okay. Right, again, how you write this is dependent on the language, the assembly language variant. So this time, I'm going to write it like this. So I'm going to put in brackets 157. Okay. So I'm saying load from the accumulator, indirect addressing 157. Right, let's change 157. So I'm going to rub out that. So I'm just doing the load accumulator one again. So I am going to put and then I'm going to say 154 has got 56. In here, I'm going to put 154. Right, so with indirect addressing, the data in the operand is a memory location. But in that memory location is some more data, and that data is a memory location. Okay? That's where the data is. Now, because we don't go into this too deep, your first question is, why would you want to do that? And it is a good valid question. You think, well, but this is complicated and it's going to be slow, so we'll see how many steps are involved. But the answer is, what it allows the hardware manufacturer to do is to specify fixed memory locations for certain standard routines that the user might want to replace. So when you're writing games, there is an interrupt. It still exists now, but it used to be really crucial from the way that TVs used to work, TV screens, CRTs. There was an interrupt that was generated when the beam had stopped drawing the screen. It was called a vertical blank or a V blank interrupt. And this was a regular thing. So at that point, there was nothing being drawn. The screen had just been drawn and you were just waiting for the phosphor to fade. As the beam moved back, that gave you time to update the position of things before the screen was drawn again. So this was a real crucial timing thing. And it is put by the CPU manufacturer at a fixed location. So it says, when V blank occurs, go to this address, look in that location, there will be a memory address where there is a routine that needs to execute. Same thing for a mouse driver. So there will be a dedicated hardware location for where the mouse driver or the keyboard driver needs to reside. Okay? We sometimes call these resident routines. So they take up space and you say, right, okay, you go there. As a user, as a programmer, I will put the location of the code I want you to run when the mouse moves or the keyboard's pressed. Okay? It allows me to change it. So if I want to write a better driver, or if I want to write a virus, or I want to write some keyboard logger, what I can do is I can update the address that's in the keyboard interrupt location, and I can say, go to my code. And then when I finish my code, I can say, oh, go off and run the actual proper keyboard driver so nobody knows what I just did, which is what a keyboard logger does. All right? But they didn't make it so you could write nefarious software. They did it so you had flexibility. So they could say, right, okay, there are certain interrupts that can generate. They will go to these locations. You need to sort out, I will set the PC to this location, set some code in there to do whatever. So you get these fixed locations. So it allows you to fix something, but then allow it to be flexible later on. Okay? Right, so in this example, we can see straight off that 56 is going to end up in the accumulator because we've followed the chain. But let's have a look at the process when we get to the execute part. I'm just going to scroll that up. Oops. I'm just going to scroll. The control key's gone on this keyboard. It didn't work very well. You know when you like don't press the centre of a key and it's not registered? Because I never press the centre of keys. Not the modified keys anyway. Right, so I'm going to start the program counter at 150. So I'm going to do step 1, transfer to the MAR. Then going to go and grab the data and put it in the MDR. So we're going to end up with LDA. And remember, in machine code, it's going to be a number. There's going to be a number to represent the addressing mode. It's what we call an effective address. And depending on how many modes you've got, you may have 2 bits or 3 bits dedicated to that. Okay, so then we copy that straight away because we say, right, we'll assume it's an instruction, copy it to the current instruction register so that when we start messing about, we're not going to lose it. Okay, so we decode it and we go, right, okay, the operand is actually a memory address. So I need to, when I come to execute, I need to say, right, okay then, so the data I need to transfer to the memory address register. Okay, so in the MAR becomes 157. Then what do I need to do?
Increment PC.
I've already incremented the PC. I'm in the execute phase now.
Oh.
So I'm trying to get everything set up so I can actually execute this instruction. Right, so I've loaded that to the MAR. What are we always going to do? There's only 2 things that I will do if I'm messing about with the MAR. What are they? Yeah?
Look in that location.
Well, let's try and use correct terminology. Read. What else might I do if I've just set the memory address register? Yeah, write. So I may issue a read or a write on the data bus. That's the only 2 things I can do. It's the only reason we use the MAR. Okay, to just do the select phase. So we're still trying to get all the data for this instruction. So we're going to do a read. Okay, so we're going to do a transfer from main store, which currently is pointing at 157, and that's going to arrive at the memory data register. The reason it's called alternatively a buffer is because it's temporary holding place. Right, so what arrives at the MDR in this case? So if we do a read from location 157, what's going to arrive at the MDR?
154.
Yeah, 154, correct. Anonymous person. Sorry about that, but you have to remain anonymous to protect your identities. You want one of those masks like I've got on that meme. I'm rambling in the video again here, where it's like, I'm AI, and underneath his mask he's got statistics or something, or whatever it is. It's something like that, isn't it? It's quite funny. And he puts the mask back on. Keep the mask. Right, okay, so we bring the 154, but the addressing mode is an indirect. So that's saying, right, well, you just fetched that, but actually that isn't the data. If that was direct addressing, that would be okay, that would be the data, but this is indirect addressing. So we're actually saying that's an address. So I want to select that location. So, right, so now I'm going to transfer, I'm not going to move it anywhere, but I'm going to say, right, transfer the MDR to the MAR. I know students get all confused with this, and they go like, how many times do you keep doing this? You say, no, this is it, just twice. Right, so we say, right, select the next. So the MAR is getting overwritten again. So now it's got 154 in it. So the control unit, working through its indirect addressing system, is going, right, okay, I've done it again. Oh yeah, I've got to do fetch. Got to fetch again. So I'm going to do another transfer. So look how many transfers we've done for this instruction. This is the 3rd transfer from main memory. Hopefully it's in the cache, but if it isn't, we're doing some slow operations. You use certain instructions sparingly. And you would hope that the compiler tries to minimize use of these sort of slow instructions for you. Depends. They don't take up much memory space as an instruction, so they're sometimes used for compactness. Right, so we're going to do a transfer to the MDR. So the MDR is having a bit of fun as well today. So what arrives at the MDR? 56. Right, and then the control unit goes, oh, great, I can actually now carry out the instruction, which was load a value to the accumulator. So it goes MDR to accumulator. And then it goes, excellent, put the 56 in there, just a quick transfer, that's quick. And then it goes, step 7, check for interrupts. So when we say there are 7 steps to the fetch execute cycle, we are generalizing. Massively generalizing. And that,
It's just one.
and what's interesting is, every time I've written that, I've made it shorter each time. I could be bothered to write 4 this time. Oh, my brain is so odd. If I could be consistent, I could probably be world ruler, but I haven't got the consistency. Although it doesn't stop some people. Right, okay, so that was indirect addressing. So, the nice thing, they ought to ask you to do this in the exam, but they don't, weirdly. They might ask you to do this, and that's quite a nice, interesting one, because you can see that the prone counter, although I didn't increment it, like anonymous person number 2 said I should have done, we can see that the current instruction register is the interesting one because it does not change from that first fetch. It's still there for the control unit to look at. Okay, that's why it's in essence, this is really a good example of what a register is. It is a dedicated storage location. It's got one job. These two get hammered, the memory address register and the memory data register, because they're select and buffer. So they're going to have lots of action depending on the types of instructions. Okay, right, the final one. What was the final addressing mode that we have to be aware of? There are loads, and it's a shame. There used to be more, and they've cut them out.
Is it indexed?
Yeah, that's the one. Indexed. Right, index addressing. Right, what's weird about index addressing? Can't remember. Right, index addressing requires 2 values. So we calculate, we specify the location of the data by combining 2 values. So index addressing, index addressing I'll tell you what, that really annoys me, that stupid bubbly stuff in the corner. I don't need to know that someone's logged in. I don't need to know I'm logged in. I know I'm logged in. So you're just annoying me. And it's making my brain think of things it doesn't want to think of. Well, it probably doesn't want to think of anything in a minute. Right, okay, so index addressing. So we need a format for this, and there are loads of different formats, but the one I'm going to use, well, I'll do it, I'll write it 2 ways. We can specify a start location and a register. Index addressing, you can't really do index addressing unless you've got a dedicated register, okay, which are often labelled with X's and Y's and things like that. In 6502 there is an X register and a Y register. In 6809 there's an IX and an IY register. So they've got these dedicated functions, okay. So you have a fixed number and you have a number that can change. That's the key thing. Okay, so we have a base. So this is described as the base. And this is the offset. Now, sometimes you specify the base using a register and you have a fixed offset. What index addressing allows us to access is table structures and array structures. So if I've got an array, in this example, stored I'm not going to use 150, that's a stupid number, because that's going to be the data. There's nothing to stop you doing that. Pointing at instructions for data, it means you can process instructions. But I didn't mean that in this example. Right, in order for this to work, we actually need another instruction to set up X. So we're just going to say LDX hash. Let's move that over. I'll do it underneath. So that's my base value. So the base is the start address of an array or whatever. Right, what would I set to access the first location? What would I set the index register to? So I've got this data at 156, so I'll put another couple of bits in there. I'm going to point the PC not there, I'm going to point it there. Right, so if I'm setting the base value as 154, what am I going to set the index register X to? Oh, I put 151. Why did no one spot that?
I saw it, I didn't know if you meant to do that or not.
No, I didn't mean to do that. Right, so I'm setting the parameter. Right, I want to access this array. There's an array. It's a string. You can see that's capital A, capital B, capital C. So this is actually a string held in memory that I'm going to process in some way. Don't know what the instructions after 150 are, I don't care. So to access that first location, if the base is 155, what would X need to be?
157. Cool.
No, I want to access that first character in this string. If the base value is 154, what am I going to add to the base to get 154? 0. So I'm going to set that up. Why have I done a comma? Right, so I'm going to use what addressing mode to set the initial value of the X register. What addressing mode do we use? Immediate. Yeah, so 0's included with the instruction. Right, so I'm setting it to 0. That will allow me to access the first element. And this is why in computer science programming, everything starts at 0. Because we're using index addressing. So we've got a base and an offset. Okay, so let's just quickly just set this up and run through it. I'm not going to fully execute. I want to get onto the instruction at 150, but I'm just going to set up the registers as if we'd executed the LDX at 149. So the MAR would have 149. Then it's going to have LDX hash naught. That's going to be transferred into the current instruction register. Right, so I'm going to have an X register that I need to keep track. And eventually, so the PC is incremented. I don't need to fetch any more data because it's immediate addressing. So an X goes in, a 0 goes into the X register. Okay, so we check for interrupts, we're good to go. So we're going to now start executing the next instruction. So we put a 150 in the MAR, we read the instruction, which is this massive thing. So LDA 154, X. We assume it's an instruction, so we copy that data to the current instruction register. Right, we then do our decode and we go, oh, it's index addressing, that's quite complicated, got to do some arithmetic here. Okay, so the first job is to work out or calculate the effective address. So we say, all right, where am I getting my data from? So it goes, right, okay, I've got to take the base value, so 154. So in order to do this, what's going to be involved? If I've got to add two values together, one's in a register and one's in the operand of the instruction, what part of the CPU is going to do the work for me? Correct. Mystery person number 3. Oh, you're mystery, not anonymous. Yeah. All right. Oh, yeah. I don't know how I did that. Mystery. You're a mystery.
So you're mystery person number 1 in that case.
Yeah, you got me there because I've started a new naming scheme and then I've screwed up my numbering. So you can be mystery person, mystery number 1, or you can be anonymous number 3. Which one do you want? Mystery 1. Okay, we'll stick with mystery 1. Right. Okay. So this is a classic my video. Ramble. Now I've lost myself. Right, okay, hang on. So mystery 1 said that we're going to use the ALU. So we need to pass to the ALU. You'll often see, if you look at diagrams of CPUs, they'll draw the ALU like this. Doing my very best, big fat V. They'll do it like this, where they've got 2 inputs and 1 output. So effectively, in order to actually just get the address this time, so that we haven't got to like go messing about on the data bus external to memory, what we need is the data part of the operand, which was 154, so let's put 154, and we need the contents of the X register, and we're going to add them together. So when we calculate that address, it's going to give us, at the end of that, 154. Okay, so the ALU has processed that, got 154. That's our memory location. So where is that 154 going to go? So it's currently in the, it's an internal accumulator, so it's not actually overwritten the accumulator doing this. But where are we going to transfer the 154? Remember, we've just calculated the address of our data. So logically, what are we going to do?
Copy to the ML.
Yeah, correct. Mystery 2. No, I'm not Mystery 2. You're confusing myself now.
No,
You are Anonymous 2. Thank you, Anonymous 2. Correct. So we're going to transfer the 154 that has just been calculated by the ALU. So from ALU, put ALU. Dear. You can't buy this sort of quality. Right, so from the ALU, I'm going to move it. I've got my finger on the control key. Stop it. I'm going to transfer that to the MAR. I don't know why I bother. To select that memory location. So the MAR has now got in it 154. What are we going to do next?
Copy whatever's in that to the ML.
Read. Issue a read command. So we don't copy. Don't try not to say copy Anonymous 2. That is going to keep amusing me now.
We should have code names.
Hey, we could do that actually. Right, have a think. For next lesson, you've got to come up with your code name.
Next to
And then I've got to try and remember them. And we could make that part of the game and the fun. Right, okay. You can have whatever. It's got to be a non-offensive term, but you've all got to come up with a code name. That is a brilliant idea, Anonymous 2, for now. Right, so we're now going to do a read. So we're going to say read from main memory at 154, because that's what's in the MAR. And it's going to arrive at the memory data register. So at 154, we arrive 65. Now this was a load instruction, so we'll load into the accumulator. So at this point, we can do a transfer MDR to accumulator. So in the accumulator, we end up with 65. Finished executing the instruction. We didn't increment the PC, but it would be 151. And then we do ints. Ints, I've just made sure on purpose. Interrupt check. Okay, now if we look at this one, the control unit couldn't do it all itself. It had to get help from the ALU. So there is another level, and what you find is that index addressing is quite slow. Okay, it's really weird on some processors. On the Motorola 6809, it's got 2 index registers, IX and IY, but the IX register is quicker. So the same instruction using the X register, not the Y register, in some circumstances is like 1 clock cycle or state quicker. Very strange. Okay, but that essentially is your little rundown of the addressing mode. So anyone got any queries about that? So